Picture this: you're floating in the infinite darkness of space, surrounded by countless pinpricks of light, each one a galaxy, home to billions of stars. But hidden at the heart of nearly every one of these galaxies lies a monster so powerful it bends the very fabric of reality: a supermassive black hole. These cosmic giants are not just voids in space, they are architects, shaping the destiny of galaxies, controlling the birth and death of stars, and holding secrets to the universe's deepest mysteries. How did these colossal beasts come to be? What strange forces lurk beyond their terrifying edges, where even light cannot escape? And what would happen if you dared to venture too close? Tonight, as you drift into relaxation, let your mind wander through the wonders of these enigmatic titans, the unseen rulers of the cosmos. Where are you joining us from, and what does the night sky look like above you right now? Close your eyes, take a deep breath, and let's journey together into the heart of darkness, where science meets the sublime. Now, let's take a moment to grasp just how enormous these cosmic giants truly are. Imagine our entire solar system, the Sun, all 8 planets, and even the distant Kuiper belt, swallowed whole by a single object. That's the scale of a supermassive black hole. While the stellar black holes you might have heard of are formed from collapsing stars and can be just tens of miles across, their supermassive cousins are mind-bendingly larger. These titans can weigh millions or even billions of times the mass of our Sun, crammed into a space smaller than our solar system. At the center of our own Milky Way galaxy, one such behemoth lurks, Sagittarius A. It's 4 million times heavier than the Sun, yet its event horizon, the point of no return, could fit comfortably within the orbit of Mercury. But Sagittarius A isn't even the largest we've found. Take the black hole in the galaxy Messier 87, for instance. Its shadow was famously captured in the first ever image of a black hole, and its mass is a staggering 6.5 billion times that of our Sun. To put it in perspective, if a typical stellar black hole were the size of a marble, a supermassive one would be as wide as a football stadium. Their sheer size warps space and time so dramatically that they don't just influence nearby stars, they dictate the fate of entire galaxies. It's almost impossible to overstate their dominance. These are not just objects in space. They are the gravitational anchors around which galaxies spin, the invisible hands shaping the cosmos itself. And yet, despite their terrifying scale, they're oddly elegant in their simplicity. No light escapes them, no sound, just pure, unfathomable gravity, bending the universe to their will. What other secrets do these giants hold? That's a journey we're just beginning to take. Now, let's unravel one of the greatest mysteries in astrophysics: how these cosmic titans came to exist in the first place. Scientists have 2 leading theories about the birth of supermassive black holes, and both paint a fascinating picture of the early universe. The first idea suggests they grew from seeds, colossal clouds of gas that collapsed directly into black holes without ever forming stars. Picture a hydrogen cloud, hundreds of thousands of times heavier than our Sun, being squeezed by gravity until it implodes into a massive dark core. These primordial seeds could have formed in the chaotic conditions just after the Big Bang, when the universe was hot, dense, and full of swirling matter. Over billions of years, they feasted on surrounding gas and stars, bulking up to the supermassive sizes we see today. The second theory proposes a more violent origin, smaller, black holes merging like cosmic snowballs. Imagine stellar black holes, the remnants of exploded stars, colliding and combining over eons. With each merger, their gravity grows stronger, pulling in more material and other black holes until they become the monsters at the heart of galaxies. Some might even argue it's a mix of both gas collapse, creating initial seeds, followed by mergers supercharging their growth. What's truly mind-blowing is that some supermassive black holes appeared shockingly early in cosmic history, barely 700 million years after the Big Bang. How they grew so big so fast remains an open question, teasing us with clues about the universe's wild youth. These formation theories aren't just academic. They shape our understanding of how galaxies, including our own, came to be. And as we peer deeper into space with powerful telescopes, we might finally catch these cosmic giants in the act of being born. Now, let's take a closer look at how these cosmic monsters bulk up to such staggering sizes. At the heart of their growth lies a process called accretion, a relentless feeding frenzy where supermassive black holes devour everything in their gravitational grip. Picture a swirling storm of gas and dust being pulled toward the black hole's event horizon. As this material spirals inward, it doesn't plunge straight in. Instead, it forms a glowing, flattened disk called an accretion disk, heating up to millions of degrees from the sheer friction and gravitational energy. These disks shine so brightly, they often outshine entire galaxies, becoming beacons visible across the universe. The physics behind this is fascinating. Matter in the disk orbits faster and faster as it gets closer to the black hole, like water circling a drain. The inner parts move at nearly the speed of light, releasing tremendous energy as X-rays and gamma rays. Some of this material does cross the event horizon, vanishing forever, while other particles get slingshotted away in powerful jets. But we'll explore those later. What's truly remarkable is how efficient this process is. A black hole can convert around 10% of the mass it consumes directly into energy, far more efficient than nuclear fusion in stars. That's why quasars, powered by supermassive black holes feeding aggressively, can blaze with the light of 1 trillion suns, despite being no larger than our solar system. But accretion isn't constant. Sometimes, black holes feast in violent bursts, triggered by collisions between galaxies or when dense gas clouds wander too close. Other times, they go dormant, like our own Milky Way's Sagittarius A star, which currently nibbles rather than gorges. Yet even in quiet phases, the potential for sudden growth remains, reminding us that these giants are never truly asleep, just waiting for their next cosmic meal. Now, let's turn our attention to one of the most spectacular displays of a supermassive black hole's power: relativistic jets. These are narrow beams of ionized matter, blasted outward at nearly the speed of light, stretching thousands or even millions of light years into space. Imagine a cosmic fire hose, but instead of water, it's shooting out particles with so much energy they can outshine entire galaxies. These jets are born from the chaos near the black hole's event horizon. Not all material in the accretion disk gets swallowed. Some of it gets caught in the black hole's powerful magnetic fields and spun into tight, high-speed streams. Like a cosmic particle accelerator, these magnetic fields launch matter outward with unimaginable force, creating the jets we observe. The impact of these jets is staggering. When they collide with surrounding gas and dust, they carve out enormous bubbles in space, heating the material to extreme temperatures and preventing it from cooling into new stars. This means black holes don't just feed, they also regulate star formation in their host galaxies, acting like cosmic thermostats. In some cases, jets can even strip away a galaxy's gas entirely, halting star birth and effectively putting the galaxy into retirement. But it's not all destruction. These jets also play a crucial role in shaping galaxy evolution. By redistributing energy across vast distances, they can trigger star formation in other regions, or even influence the growth of neighboring galaxies. It's a delicate balance, one that scientists are still unraveling. And here's something truly mind-bending. Because these jets move so close to light speed, time behaves differently for them. From our perspective, they might appear to move faster than light, though they never actually break the cosmic speed limit. It's just another reminder of how black holes twist the very fabric of reality around them. What's next? Well, these galactic giants don't just shape their surroundings, they dominate them. And that leads us to their reign at the heart of galaxies. Now, let's zoom out from those incredible jets and consider where they originate, the very heart of galaxies. Supermassive black holes don't just lurk in space. They anchor entire galaxies, sitting at their cores like cosmic monarchs. The Milky Way is no exception. At its center lies Sagittarius A star, a supermassive black hole with a mass of over 4 million times that of our Sun. These colossal objects exert an almost unimaginable gravitational pull, dictating the movements of stars, gas, and dust around them. Picture a whirlpool, with everything in its vicinity slowly spiraling inward. But here's the twist. Most stars and planets don't actually fall in. Instead, they orbit the black hole in a stable dance, much like Earth circles the Sun, only on a far grander scale. The influence of these black holes extends far beyond their immediate surroundings. Their gravity shapes the entire structure of their host galaxies, influencing how stars form and cluster. Some galaxies even have multiple supermassive black holes, remnants of ancient cosmic collisions where galaxies merged, but their central black holes never fully combined. These binary or triple systems create even more complex gravitational scenarios, warping space in unpredictable ways. And while we often think of black holes as destructive forces, their presence might actually be essential for galaxies to exist at all. Without the stabilizing effect of a central supermassive black hole, galaxies could become unstable, their stars scattered into the void. It's a delicate cosmic balance, one where the universe's most feared objects might also be its greatest architects. So what's next in this cosmic story? Well, let's peer even closer to the edge of these mysterious giants, right to the point where not even light can escape. Now, Imagine stepping closer to the edge of the unknown, the event horizon, the ultimate boundary where the black hole's grip becomes inescapable. This is the point of no return, the invisible line where gravity wins the battle against anything that dares to cross it, even light itself. At the event horizon, the black hole's pull is so intense that the speed needed to escape exceeds the speed of light. Since nothing in the universe can go faster than light, anything that passes this threshold is doomed to fall inward. The physics here bends our understanding of reality. Time slows to a crawl for an outside observer watching something approach the event horizon, while for the object itself, the plunge happens in what feels like an instant. So what happens to matter and light that cross this boundary? Picture a cosmic shredder. As material spirals in, tidal forces stretch and compress it in a process called spaghettification, turning stars, gas, or even planets into long, thin streams of particles. These fragments heat up to unimaginable temperatures, emitting intense radiation before vanishing into the black hole's depths. Meanwhile, the light that crosses the event horizon doesn't just disappear, it's trapped forever, adding to the black hole's mass and making it even more formidable. But here's the strangest part. To an outside observer, the infalling material never seems to fully cross the event horizon. Instead, it appears to freeze at the edge, fading from view as its light stretches into longer, redder wavelengths. This illusion is a trick of gravity, warping space and time, making the black hole's surface seem like a cosmic still image. The event horizon isn't just a physical boundary, it's a frontier where the known laws of physics begin to unravel. And beyond this edge lies a mystery we're still striving to understand. So what lies deeper? That's a question that takes us to the heart of a black hole's greatest secrets. Now, let's take a journey into one of the most mind-bending consequences of a black hole's gravity, the way it warps time itself. Picture this: you're watching a spacecraft inch closer to a black hole's event horizon. To you, the observer, its movements slow down, as if time itself is dragging. But for the astronauts on board, time feels normal. This isn't science fiction. It's Einstein's theory of relativity in action. Near a supermassive black hole, gravity is so powerful that it literally stretches time. Think of it like a cosmic treadmill. The closer you get, the harder time has to work to keep up. For someone far away, watching a clock near the black hole, its ticks would appear to slow to a crawl. But for the clock itself, nothing changes. This bizarre effect, called time dilation, shows just how much black holes twist the fabric of reality. Einstein gave us a way to understand this with his famous thought experiment. Imagine twins, one staying on Earth, the other traveling near a black hole. When the spacefaring twin returns, they'd be younger than their Earth-bound sibling. Time pass slower for them. That's because gravity doesn't just pull on objects, it bends time itself. Near a black hole, this bending becomes extreme, turning seconds into years for distant observers. But here's where it gets even stranger. If you could hover just outside the event horizon, time would slow so much that you'd see the entire future of the universe unfold in what feels like moments. Galaxies would age, stars would burn out, and cosmic history would rush by like a sped-up film. Yet for you, time would creep forward, a prisoner of the black hole's relentless pull. This isn't just theoretical. Scientists have measured time dilation in weaker gravitational fields, like Earth's. GPS satellites, for example, have to account for tiny time shifts caused by our planet's gravity. But near a black hole, the effect is so dramatic it defies intuition. Time doesn't just slow, it becomes a fluid, stretchable thing, reshaped by the universe's most extreme environments. So next time you glance at a clock, remember time isn't as fixed as it seems. Near a black hole, it's a relative experience, bending to the will of gravity's invisible hand. And that's just the beginning of the cosmic oddities these giants hold. Now, let's shift our focus to something even more unsettling: the violent forces that await anything that falls too close to a black hole. Imagine you're floating toward one of these cosmic monsters feet first. At first, everything feels normal, but as you get closer, an invisible hand starts pulling at your toes harder than your head. The difference in gravity between your feet and your head becomes so extreme that your body begins to stretch like taffy. This is the nightmare of tidal forces. Just as the moon's gravity creates tides on Earth, a black hole's gravity tugs on anything nearby, but with unimaginable strength. The closer you get, the more extreme the pull. Your legs would stretch first, elongating like spaghetti, while your arms get wrenched sideways. Even the strongest materials wouldn't stand a chance. Stars, planets, or spacecraft, everything gets shredded in a process scientists grimly call spaghettification. Here's how it works. Every object has a center of mass, and gravity pulls hardest on the side closest to the black hole. For something as small as a human, the difference in pull between your head and feet would be catastrophic. Your body would stretch thinner and thinner until, well, let's just say it wouldn't be pleasant. But even for something as massive as a star, the outcome is the same. Astronomers have watched stars get torn apart by black holes, their material stretched into glowing streams before vanishing past the event horizon. What's wild is that this isn't just some brutal cosmic accident. It's physics in action. The same tidal forces that gently lift ocean waves on Earth become monstrous near a black hole because gravity's grip increases exponentially the closer you get. A supermassive black hole might spare you from spaghettification longer than a smaller one, but make no mistake, get too close, and gravity will always win. So the next time you boil pasta, remember out there in the cosmos, black holes are doing the same thing to entire stars. Only instead of al dente, the result is a stream of superheated plasma spiraling into the abyss. And that's just another reminder of how these cosmic giants don't just bend space and time. They shred reality itself. Now, let's take a step back from the terrifying pull of black holes and marvel at something equally astonishing: our ability to actually see them. Or at least their shadows. In 2019, scientists made history by capturing the very first image of a black hole's shadow, a groundbreaking moment that felt like science fiction coming to life. The black hole in question sits at the heart of the galaxy Messier 87, 55 million light-years away, and the image, a fiery orange ring with a dark void at its center, instantly became one of the most iconic snapshots in astronomy. So how did we manage to photograph something that, by definition, doesn't let light escape? The answer lies in the black hole's shadow, not the black hole itself. As matter swirls around the event horizon, it heats up to incredible temperatures, glowing intensely. This glowing material forms what's called an accretion disk, and it's this disk that outlines the black hole's shadow, the absence of light, where the event horizon hides. The dark center isn't the black hole's surface, but rather the point where light vanishes forever. Capturing this image wasn't as simple as pointing a telescope at the sky. The Event Horizon Telescope, or EIT, is actually a network of radio telescopes scattered across the globe, from Hawaii to the South Pole. By synchronizing these telescopes, scientists created a virtual telescope as large as Earth itself, a technique called very long baseline interferometry. This gave them the resolution needed to see details as fine as a donut on the moon. Over several nights, these telescopes collected petabytes of data, which then took years to process and transform into that now famous image. What makes this achievement even more remarkable is the sheer scale of the challenge. M87's black hole is massive, about 6.5 billion times the mass of our Sun, but from Earth, it appears tiny in the sky. Spotting it was like trying to read the date on a coin from thousands of miles away. Yet, the EHT pulled it off, not only confirming decades of theoretical predictions, but also giving us a stunning visual of one of the universe's most mysterious objects. This image isn't just a scientific trophy, it's a window into understanding how black holes bend light, distort space, and shape their surroundings. And as the EHT continues to refine its technology, who knows what other cosmic secrets we'll uncover next. But there's another dazzling spectacle in the cosmos that ties directly to these supermassive black holes, quasars. Imagine an object so bright it can outshine an entire galaxy, yet it's no larger than our solar system. That's the mind-bending reality of quasars, and they owe their brilliance to the same cosmic giants we've been exploring. At the heart of every quasar lies a supermassive black hole, but not just any black hole, one that's feasting voraciously on surrounding gas and dust. As this material spirals inward, it doesn't just vanish quietly. Instead, it heats up to millions of degrees, creating an accretion disk that glows with unimaginable intensity. The energy released is so staggering that quasars can be seen clear across the universe, even when their host galaxies fade into obscurity. In fact, the brightest quasars shine thousands of times brighter than the Milky Way, making them the most luminous objects in the known cosmos. What's even more fascinating is that quasars are just one type of active galactic nucleus, or AN. These are the energetic cores of galaxies, where supermassive black holes are actively devouring matter. Some AGNs, like quasars, are visible from billions of light years away because their jets and radiation are pointed directly at us. Others might be hidden behind thick clouds of dust, their light dimmed but their power undiminished. Scientists believe quasars were far more common in the early universe, when galaxies were younger and packed with fresh gas for black holes to consume. Today, most supermassive black holes are relatively quiet, having exhausted their nearby fuel. But when we observe distant quasars, we're essentially looking back in time, witnessing the universe in its most explosive and energetic youth. These cosmic beacons don't just light up the sky, they also shape their surroundings. The intense radiation and powerful jets from quasars can heat up interstellar gas, preventing it from collapsing into new stars. In a way, quasars act as cosmic regulators, controlling the growth of their host galaxies. It's a reminder that even the most distant, brilliant objects are deeply connected to the evolution of the universe itself. So the next time you hear about a quasar, remember, it's not just a distant point of light. It's a supermassive black hole in its most dazzling outfit, showing us just how dynamic and interconnected the cosmos truly is. But now, let's turn our attention to one of the most fascinating roles these cosmic giants play, acting as thermostats for their galaxies. Supermassive black holes don't just consume matter mindlessly. They also give back in ways that shape the very fabric of their surroundings. When a black hole feeds, it doesn't just swallow everything silently. Some of the material gets funneled into those powerful jets we talked about earlier, blasting away at near light speed. These jets, along with intense radiation from the accretion disk, heat up the surrounding gas in the galaxy. Now, here's where things get interesting. That heated gas can't cool down easily, which means it can't collapse to form new stars. It's like turning up the thermostat in a room so high that water vapor never condenses into droplets. The black hole, in a way, puts a lid on star formation, controlling how fast its galaxy grows. But sometimes, the effect is even more dramatic. The energy from the black hole can push gas entirely out of the galaxy, stripping away the raw material needed for future stars. Imagine a cosmic wind so strong, it sweeps away the building blocks of solar systems before they can even take shape. This process, known as feedback, is why some galaxies stop forming stars altogether. They're not just aging gracefully, they've had their star-making fuel forcibly removed by their central black hole. What's truly remarkable is the balance at play here. Without this feedback, galaxies would churn out stars uncontrollably, burning through their gas too quickly. But with too much feedback, they'd run out of star-forming material entirely. Supermassive black holes, in their own violent way, help maintain a cosmic equilibrium. They're not just destroyers, they're regulators, ensuring galaxies grow at a sustainable pace. So the next time you think about black holes, remember, they're not just lurking in the shadows, they're active participants in the life cycle of galaxies, turning the knobs on star formation like master cosmic engineers. And in doing so, they shape the universe we see today. But beyond the visible effects of black holes, there's an even deeper mystery lurking in the shadows. Scientists are now exploring the intriguing possibility that supermassive black holes might have a hidden connection to dark matter, the invisible glue that holds galaxies together. Dark matter makes up about 85% of the universe's mass, yet we can't see it directly. It doesn't emit light or energy, but its gravitational pull shapes the motion of stars and galaxies. Now, here's where black holes come in. Some researchers believe these cosmic giants could be surrounded by dense clouds of dark matter, or might even interact with it in ways we don't yet understand. One theory suggests that dark matter particles could be captured by a black hole's immense gravity, slowly accumulating over time and influencing how the black hole grows. Others speculate that black holes themselves might be made of exotic forms of dark matter, or that their jets could be shaped by unseen dark matter halos. While these ideas are still speculative, they open up thrilling possibilities about the hidden forces at work in our universe. Recent studies have even looked for clues in the way black holes move. Some supermassive black holes appear to wobble slightly in their orbits, and scientists wonder if this could be due to dark matter's gravitational tug. It's like trying to sense an invisible hand by watching how a dancer moves, subtle but potentially revealing. As telescopes grow more advanced and simulations more detailed, we're inching closer to answers. The relationship between black holes and dark matter might just hold the key to unlocking some of the universe's biggest secrets. And if we solve this puzzle, we won't just understand black holes better, we'll grasp the very fabric of the cosmos itself. So while dark matter remains elusive, its possible ties to supermassive black holes remind us that the universe still has plenty of surprises in store. Every discovery peels back another layer, revealing just how much we have yet to learn. Now, let's turn back the cosmic clock to the very beginning. Among the many mysteries surrounding supermassive black holes, one of the most fascinating is the idea that some of them might not have formed the way we once thought. Instead of growing slowly over billions of years, they could have sprung into existence almost instantly in the chaos of the early universe. This is the primordial black hole theory. Picture the universe just moments after the Big Bang, a seething, dense soup of energy and matter. In some regions, extreme fluctuations in density might have created pockets so intense that they collapsed directly into black holes. Unlike the ones formed from dying stars, these primordial black holes could have been born with enormous masses right from the start, seeding the supermassive giants we see today. What makes this idea so compelling is that it could solve a cosmic puzzle. Some supermassive black holes, like those powering the most distant quasars, appear fully grown when the universe was barely a billion years old. That's not enough time for them to form through normal processes, like gobbling up gas or merging with smaller black holes. But if they were already massive from the beginning, their existence suddenly makes sense. Of course, this theory isn't without its challenges. For one, the conditions needed to create primordial black holes are incredibly exotic. We're talking about an infant universe where gravity and quantum effects were tangled in ways we still barely understand. And while we haven't found direct evidence yet, scientists are hunting for clues like the faint gravitational waves these ancient black holes might have left behind, or the subtle distortions they could cause in the cosmic microwave background. If primordial black holes do exist, they wouldn't just rewrite the story of how supermassive black holes came to be. They could also help explain dark matter, or even the strange ripples in space-time we detect today. It's a reminder that the early universe was a laboratory of extremes, where the rules of physics were pushed to their limits. And as we peer deeper into the past, we might just uncover answers that reshape our understanding of everything. Now, let's shift our gaze to one of the most dramatic events in the cosmos, the explosive mergers of supermassive black holes. Imagine two of these behemoths, each weighing millions or even billions of times more than our sun, locked in a gravitational dance. As they spiral closer, their immense gravity warps space and time, sending ripples across the universe like waves from a stone dropped in a pond. These ripples are gravitational waves, and they carry the story of the collision across billions of light years. What makes these mergers so extraordinary isn't just the scale, it's the energy. When two supermassive black holes finally collide, they release more power in an instant than all the stars in the observable universe combined. That energy doesn't vanish, it radiates outward as gravitational waves, stretching and squeezing space itself as they pass through it. And thanks to groundbreaking instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, we can now detect these cosmic tremors. LIGO's role in this discovery is nothing short of revolutionary. By using lasers to measure tiny distortions in space-time, changes smaller than the width of an atom. Chinese letter, 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 Chinese letter. Each detection is like opening a window into the universe's most violent events, revealing details about the black hole's masses, spins, and even how they form. But here's the fascinating part. These mergers don't just tell us about black holes. They also test Einstein's theory of relativity in extreme conditions. So far, every ripple LIGO has detected matches his predictions, proving that even in the chaos of a black hole collision, the laws of physics hold firm. Yet mysteries remain. For instance, how do supermassive black holes even get close enough to merge? Some might be pushed together when galaxies collide, while others could be nudged by vast streams of gas or the pull of dark matter. And while LIGO has spotted smaller black holes merging, catching a supermassive pair in the act is the next big goal, one that could unlock secrets about how galaxies evolve. Every collision we detect is a piece of a larger puzzle, helping us understand not just black holes, but the very fabric of the cosmos. And as our tools grow more advanced, who knows what other cosmic symphonies we'll hear echoing through the void. But beyond the chaos of their collisions, supermassive black holes hold a quieter, equally profound secret: their cosmic time capsules, preserving echoes of the universe's earliest days. Think of them as ancient librarians, guarding records written not in ink, but in gravity and light. By studying these giants, astronomers can peel back layers of cosmic history, uncovering clues about how galaxies formed, stars ignited, and the universe itself evolved. Take the way a black hole's surroundings absorb and emit light. For example, the gases swirling around its edges carry chemical fingerprints of their origins, some dating back to when the first stars blazed to life. By analyzing these signatures, scientists can piece together what the universe was like billions of years ago, like reading pages from a diary frozen in time. Then there's their incredible longevity. While stars burn out and galaxies fade, supermassive black holes endure, often unchanged for eons. Their sheer stability makes them perfect benchmarks for measuring how the cosmos has shifted over time. By comparing ancient black holes to younger ones, researchers can track changes in the universe's expansion rate, the growth of cosmic structures, even the behavior of dark energy, all from these gravitational anchors. And let's not forget their role as storytellers of cosmic violence. The scars left by ancient mergers, the distortions in their accretion disks, even the trajectories of stars orbiting them, all hint at past collisions, feasts, and upheavals that shaped their home galaxies. It's like piecing together a dinosaur's life from its bones, but on a scale so vast, it spans entire galactic lifetimes. So while they may seem like destructive forces, supermassive black holes are also meticulous historians. Every flicker of light, every ripple in space-time, even their silent gravitational pull, it all whispers secrets about where we came from and how the universe grew into what we see today. And as we learn to listen more closely, who knows what other chapters of cosmic history we'll uncover. Now, let's turn to one of the most puzzling mysteries surrounding black holes, the information paradox. This cosmic conundrum challenges our very understanding of reality, blending physics and philosophy in a debate that even the brightest minds can't fully resolve. At its heart lies a simple yet profound question. When something falls into a black hole, is the information about it truly lost forever? Stephen Hawking brought this paradox into sharp focus with his groundbreaking work. He argued that black holes aren't entirely black. They emit a faint glow, now called Hawking radiation, which slowly causes them to evaporate over unimaginable timescales. But here's the catch. If a black hole vanishes, what happens to all the information about the stars, gas, and planets it swallowed? According to the laws of quantum mechanics, information can't simply disappear. It must be preserved somehow. Yet Hawking's calculations suggested the opposite, sparking a decades-long scientific tug of war. Some physicists believe the information is scrambled and eventually released as the black hole evaporates, like burning a book, but leaving behind ashes that, in theory, could be reassembled. Others propose it's encoded in the black hole's event horizon, a vast cosmic ledger storing every detail of what fell inside. Then there's the wilder idea that information escapes into an entirely new universe, a hidden dimension beyond our own. Hawking himself later revised his stance, suggesting information might leak back out, but the debate rages on. Experiments remain impossible for now, leaving scientists to wrestle with equations and thought experiments. It's a puzzle that forces us to rethink the fundamental nature of space, time, and reality itself, one where even the rules of quantum physics and gravity seem to clash. So while we don't have all the answers yet, the information paradox reminds us that black holes aren't just cosmic vacuum cleaners. They're laboratories for the most extreme physics, pushing the boundaries of what we know and challenging us to ask deeper questions about the universe. And who knows, solving this paradox might just unlock the next great leap in our understanding of reality. Now, let's venture into one of the most thrilling ideas in modern physics. Could black holes actually be gateways to other parts of the universe, or even other dimensions? This brings us to the mind-bending concept of wormholes, cosmic tunnels that could connect distant points in space and time. While wormholes remain purely theoretical for now, scientists speculate that they might be linked to the extreme physics of black holes, offering potential shortcuts across the cosmos. The idea isn't just science fiction. Einstein's theory of general relativity actually allows for the existence of wormholes, mathematically speaking. Picture space as a folded sheet of paper. A wormhole would act like a tunnel, piercing through that fold, letting you jump from one side to the other in an instant. Now, imagine if some supermassive black holes held the entrance to such a tunnel. The problem: these hypothetical wormholes would be incredibly unstable, likely collapsing the moment anything tried to pass through. To keep a wormhole open, you'd need something called exotic matter, a substance with negative energy that defies gravity's pull. No such material has ever been found, but its existence could theoretically prevent the wormhole from snapping shut. Even more intriguing, some models suggest that if wormholes do exist, they might not just bridge space, they could connect different times, turning them into time machines. Of course, the dangers are as extreme as the possibilities. Falling into a black hole, even one hiding a wormhole, would likely tear you apart long before you reach the other side. And if you somehow survived, there's no guarantee where or when you'd end up. Still, the idea fuels our imagination. Could advanced civilizations, if they exist, have mastered wormhole travel? Might the universe be threaded with hidden tunnels we've yet to detect? For now, these questions remain unanswered, but they remind us of something profound. Black holes aren't just destructive monsters. They might also hold the keys to the universe's greatest mysteries, from interstellar shortcuts to the very fabric of space-time itself. And as our understanding grows, who knows what incredible discoveries might be waiting just beyond the event horizon. Let's shift our perspective and explore something equally fascinating: the invisible rules that govern black holes themselves. Just like stars or planets, black holes follow their own set of physical laws, and understanding these can reveal even more about how they shape the universe. At the heart of black hole thermodynamics is a startling idea. Black holes aren't just cosmic vacuums. They have temperature, they emit energy, and they even have entropy, a measure of disorder. This might sound impossible, since nothing is supposed to escape a black hole's grip. But thanks to Stephen Hawking's groundbreaking work, we now know that black holes can, in fact, lose energy over time through a process called Hawking radiation. Here's how it works. Near the event horizon, pairs of particles and antiparticles constantly pop in and out of existence, as they do everywhere in space. Normally, these pairs annihilate each other instantly, but if one particle falls into the black hole while the other escapes, the black hole loses a tiny bit of mass in the process. Over unimaginably long timescales, this slow leak could cause a black hole to evaporate entirely. Then there's entropy. Black holes have an enormous amount of it, so much that it's directly tied to the size of their event horizons. The larger the black hole, the more entropy it contains. This creates a strange parallel between black holes and thermodynamics, linking gravity to the laws of heat and energy in ways physicists are still unraveling. What's truly mind-bending is that black holes seem to obey laws eerily similar to those of thermodynamics. For instance, they can't decrease in entropy, just like heat can't flow from a cold object to a hot one without external work. This hints at a deeper connection between gravity, quantum mechanics, and the fundamental fabric of reality. So while black holes might appear as simple, dark voids, they are actually dynamic objects governed by complex, invisible rules. And with every discovery, we're not just learning about black holes, we're uncovering the hidden laws that might dictate the fate of the entire universe. Now, let's turn our attention to the remarkable tools that allow us to study these mysterious giants. Even though they themselves remain invisible, astronomers have developed ingenious ways to observe supermassive black holes, relying on the clues they leave behind in the fabric of space. One of the most powerful tools in this quest is the radio telescope. These colossal dishes pick up the faint radio waves emitted by the chaotic activity around black holes, particularly from their jets and accretion disks. The Event Horizon Telescope, a global network of radio telescopes, made history by capturing the first ever image of a black hole's shadow in the galaxy Messier 87. By synchronizing telescopes across the planet, astronomers created a virtual dish as large as Earth itself, sharpening their view enough to see the outline of a black hole's event horizon. Then there are X-ray observatories like NASA Chandra X-ray Observatory and the European Space Agency's Newton. These instruments detect high-energy X-rays produced by the superheated gas spiraling into black holes. When matter gets close to the event horizon, it heats up to millions of degrees, glowing brightly in X-rays and revealing the black hole's presence. Without these observatories, we'd miss some of the most dramatic signatures of black hole activity. Infrared telescopes also play a crucial role. They peer through cosmic dust to study stars orbiting perilously close to supermassive black holes, like those near Sagittarius, a star at the Milky Way's center. By tracking these stars' movements over years, astronomers can measure the black hole's mass and map its gravitational grip. And let's not forget gravitational wave detectors like LIGO and Virgo. While they are best known for detecting colliding stellar mass black holes, future upgrades could spot mergers of supermassive black holes, giving us a front row seat to the universe's most energetic events. Each of these tools offers a different piece of the puzzle, helping us assemble a clearer picture of how black holes behave, grow, and shape their surroundings. What's truly exciting is that as technology advances, so does our ability to uncover the secrets of these cosmic giants. Now, let's uncover one of the most fascinating mysteries in modern astrophysics: how supermassive black holes may have played a pivotal role in the birth of galaxies themselves. For decades, astronomers puzzled over a chicken and egg question. Did galaxies form first, giving rise to black holes at their centers, or did the black holes emerge early, acting as seeds that pulled galaxies into existence around them? The answer, it turns out, might be a bit of both. In the early universe, vast clouds of gas and dark matter began collapsing under gravity, forming the first protogalaxies. Some theories suggest that supermassive black holes formed at the same time from dense pockets of matter, growing rapidly as they fed on the surrounding chaos. These black holes then unleashed powerful jets and radiation, heating the gas around them and regulating how quickly stars could form. Without this influence, galaxies might have burned through their fuel too quickly, leaving them stunted and unstable. But the black hole's role didn't stop there. Their immense gravity also shaped the motion of stars and gas, sculpting the galaxies into the spiral and elliptical forms we recognize today. In some cases, Violent mergers between galaxies funneled even more material toward their central black holes, triggering bursts of star formation and creating the colossal elliptical galaxies we see in the modern universe. What's truly remarkable is the harmony between black holes and their host galaxies. Observations show that the mass of a galaxy's central black hole is closely tied to the size of its central bulge of stars, a clue that the two grew together, influencing each other over billions of years. This cosmic partnership suggests that black holes aren't just passive inhabitants of galaxies, but active architects, helping to shape the very structures that define our universe. And as we peer deeper into space with telescopes like the James Webb, we're uncovering even more clues about how this intricate dance unfolded in the universe's infancy. The story of galaxy formation is far from complete, but one thing is clear: supermassive black holes have been pulling the strings behind the scenes, shaping the cosmos in ways we're only beginning to understand. Now, let's venture into one of the most puzzling frontiers of modern cosmology: the possible link between supermassive black holes and dark energy, the mysterious force driving the universe's accelerating expansion. At first glance, these two cosmic phenomena might seem unrelated. One is a gravitational monster lurking in galaxies, while the other is an invisible energy stretching space itself. But some scientists suspect there's a hidden connection, and if proven true, it could rewrite our understanding of the universe. The puzzle begins with dark energy's most startling effect. It's causing the universe to expand faster over time, pushing galaxies apart as if space itself has a repulsive force. Strangely, this acceleration only became dominant a few billion years ago. Around the same time, supermassive black holes finished their most intense growth phases. Coincidence? Maybe not. One controversial theory suggests that black holes might store vacuum energy, a form of energy tied to empty space, and as they grow, they release this energy into the cosmos, contributing to dark energy's push. Another idea proposes that black holes could be portals to an even deeper mystery. Some models of quantum gravity hint that the cores of supermassive black holes might contain peculiar states of matter or energy that leak outward, subtly influencing the expansion of space on cosmic scales. While these ideas remain speculative, they offer a tantalizing possibility that black holes aren't just shaping galaxies, but may be shaping the very fabric of the universe itself. Of course, not all scientists agree. Skeptics argue that the connection is circumstantial, with no direct evidence yet linking black holes to dark energy's behavior. But the debate is far from settled. New observations, like measurements of black hole mergers or the universe's expansion rate, could tip the scales in favor of one theory over another. What makes this idea so compelling is its sheer audacity. If supermassive black holes truly play a role in dark energy's influence, it would mean these cosmic giants are even more powerful than we imagined, not just sculptors of galaxies, but possibly architects of the universe's fate. As researchers dig deeper into this cosmic enigma, one thing is certain: the story of black holes is still being written, and the next chapter might just redefine everything we know. But now, let's turn our attention to a different kind of cosmic traveler: the rogue supermassive black holes wandering through the vast emptiness between galaxies. These are not the stationary giants we've come to expect, anchored at the hearts of galaxies. Instead, they've been violently flung into the void, embarking on solitary journeys across the cosmos. How does a black hole, billions of times the mass of our Sun, get ejected from its home galaxy? The answer lies in the chaotic dance of galaxy collisions. When two galaxies merge, their central black holes spiral toward each other, locked in a gravitational embrace. Sometimes, instead of merging, the immense energy of their interaction can slingshot one of them outward at incredible speeds, fast enough to escape the galaxy entirely. Imagine a supermassive black hole, once the ruler of a bustling galactic center, now drifting alone through the darkness. With no stars or gas to feed on, these wanderers become nearly invisible, detectable only by the faint ripples they leave in the fabric of space-time. Yet their presence hints at dramatic cosmic events, violent mergers that reshaped entire galaxies and left these giants homeless. What's even more fascinating is that these rogue black holes might not be entirely alone. Some could carry a small cluster of stars, torn away from their original galaxy during the ejection. These stars, bound by the black hole's gravity, would form a faint, trailing glow, a ghostly reminder of the home they left behind. While intergalactic wanderers are rare, their existence teaches us something profound about the universe. Even the mightiest objects are not immune to the forces of chaos. And as they drift through the cosmic void, they remind us that the universe is far more dynamic and unpredictable than we often imagine. Next time you look up at the night sky, consider this: somewhere out there, a lonely supermassive black hole is moving silently through the darkness, a relic of a galactic collision that happened billions of years ago. And who knows, one day, our own Milky Way might fling its supermassive black hole into the abyss, adding another wanderer to the cosmic sea. Now, let's journey back in time to the very origins of these cosmic giants. The mystery of how supermassive black holes grew so large so quickly has led scientists to an intriguing idea: the black hole seed theory. Imagine the early universe, just a few 100 million years after the Big Bang. In this primordial soup of gas and energy, conditions were unlike anything we see today. The first black holes may have formed from direct collapses, where enormous clouds of gas, free of contaminating heavier elements, collapsed under their own gravity without ever forming stars first. These would have been the seed's black holes, born already thousands of times more massive than the ones formed from dying stars. With such a head start, they could quickly grow by devouring the dense gas surrounding them, ballooning into the supermassive giants we observe in the young universe. Some might argue that stellar black holes could have merged repeatedly to reach such sizes, but the seeds theory offers a simpler explanation for why we see fully grown, supermassive black holes when the universe was still in its infancy. What's truly fascinating is that these seeds might still exist today, hidden relics of the early cosmos. Some could be lurking at the centers of dwarf galaxies, overlooked because they haven't grown as dramatically as others. Others might have been ejected during galactic collisions, becoming the very intergalactic wanderers we just discussed. This theory reshapes our understanding of cosmic history. If the first black holes grew from seeds rather than stars, It means the universe had a completely different pathway to creating these monsters, and with new telescopes peering deeper into space and time than ever before, we might soon find the evidence that settles this cosmic debate. Now, let's step into the virtual universe, where scientists use supercomputers to bring black holes to life. These powerful machines don't just crunch numbers, they paint vivid simulations of how these cosmic giants behave, revealing secrets no telescope could see on its own. Imagine feeding the laws of physics into a digital realm, where gravity twists space and time, and black holes devour matter in dazzling whirlpools of light. Supercomputers like NASA Pleiades or the National Science Foundation's Frontier simulate millions of years of cosmic activity in weeks. They show us how gas swirls into an accretion disk, how jets blast outward at near light speed, even what happens when two supermassive black holes collide. One groundbreaking simulation showed something unexpected: black holes might not always merge smoothly. Sometimes they get stuck in a gravitational dance for thousands of years, trapped in what scientists call the final parsec problem. Other models reveal how black holes fling stars across galaxies like cosmic slingshots, or how their shadows warp under extreme gravity. But these simulations aren't flawless. They rely on our current understanding of physics, which means every mystery solved could uncover new questions. For instance, when simulations of the early universe produce black holes too small or too few, it hints that our theories might need tweaking. That's the beauty of this digital detective work. It doesn't just answer questions, it shows us where to look next. As supercomputers grow faster and models sharper, we're inching closer to demystifying these enigmatic giants. Each simulation is like a time machine, peeling back layers of cosmic history, one calculation at a time. And with every breakthrough, we rewrite the story of the universe itself. Now, picture the chaotic realm just outside a supermassive black hole, a place where the universe turns up the heat. These extreme environments are like cosmic pressure cookers, where gravity's grip warps everything in its path. Imagine clouds of gas, superheated to millions of degrees, swirling in a frantic dance before vanishing into the abyss. This isn't just hot, it's plasma so intense it glows brighter than 1,000 suns, lighting up the darkness around the black hole like a beacon. But the heat is only the beginning. Magnetic fields here don't just bend, they twist into impossible knots, powerful enough to launch jets of particles across entire galaxies. Think of them as cosmic railguns, accelerating matter to nearly the speed of light. And all this happens while tidal forces stretch and squeeze anything that ventures too close, turning stars into streaks of luminous spaghetti. Even empty space isn't safe. Quantum effects near the event horizon create a storm of virtual particles popping in and out of existence. Some get swallowed, while others escape as Hawking radiation, a faint whisper of the black hole's slow evaporation. It's a battlefield where the laws of physics are pushed to their limits, and yet, amid this violence, black holes shape the galaxies around them. What's truly astonishing is how these extreme conditions aren't just destructive, they're creative. The same forces that tear matter apart also seed new stars, sculpting the universe in ways we're only beginning to understand. So next time you look up at the night sky, remember, the darkest places in space might just be the most brilliant factories of change. As we peer into the cosmic frontier, the next era of black hole exploration is just beginning. Groundbreaking missions are set to unveil secrets these giants have kept hidden for billions of years. Take LISA, the Laser Interferometer Space Antenna, for example. This ambitious project will float in space like a delicate web of lasers, designed to catch the faintest ripples of gravitational waves from colliding supermassive black holes. Unlike Earth-bound detectors, LISA sensitivity could reveal mergers from the universe's earliest chapters, events so ancient they predate even the first stars. Then there's the James Webb Space Telescope, our infrared eye in the cosmos. Already revolutionizing astronomy, Webb's piercing gaze can spot the faint glow of matter spiraling into distant black holes, even through cosmic dust that once hid them from view. Imagine catching a black hole in the act of feasting, watching how its meal alters its surroundings in real time. Webb might even spot the birth cries of supermassive black holes in infant galaxies, helping us solve the puzzle of how they grew so big so fast. But the surprises don't stop there. Upcoming X-ray observatories will map the scorching plasma around black holes with unprecedented detail, while radio telescope arrays sharper than ever could snap portraits of more event horizons, perhaps even capturing our own Milky Way's black hole mid-burp as it swallows a gas cloud. What ties these missions together is a single thrilling possibility. They might finally show us how black holes and galaxies grew up together, entwined in a cosmic dance. With every new observation, we're not just collecting data, we're rewriting the story of the universe itself. And who knows, the next decade of discoveries could reveal that black holes are even stranger, even more vital to the cosmos than we ever dreamed. Now, let us step back and consider something even more profound. Supermassive black holes don't just shape galaxies, they challenge the very foundations of how we perceive reality. Picture this: near the event horizon, time doesn't just slow down. It warps, bends, and practically grinds to a halt relative to the outside universe. For someone falling in, minutes might pass, while out here, centuries fly by. This isn't science fiction, it's Einstein's relativity in action, forcing us to question what time even means. Then there's space itself. A black hole's gravity is so intense that it twists the fabric of the cosmos like a rubber sheet stretched to its limit. Directions lose meaning. Up, down, left, right. None of it matters when space is this distorted. It's as if the universe rewrites its own rules, leaving us to wonder, is reality as solid as we think, or just a set of conditions that can be bent and broken? And what about existence? When matter crosses the event horizon, it's gone, not just hidden, but erased from our universe in a way that defies conventional physics. This sparks the infamous information paradox. If black holes destroy information, do they unravel the predictability at the heart of science? Even Stephen Hawking wrestled with this, proposing that black holes might leak radiation over eons, hinting at answers we don't yet have. Perhaps the most humbling thought is this: black holes expose the limits of human knowledge. They're cosmic riddles, reminding us that for all our theories and telescopes, the universe still holds mysteries beyond our grasp. They invite us to keep questioning, to stay curious, because every enigma we solve only reveals deeper ones waiting in the dark. And as we ponder these giants, we're left with a final, haunting question. Could black holes be doorways to something even stranger, or are they the ultimate dead end? The answer, like the black holes themselves, remains just out of reach. But beyond the science and the cosmic mysteries, black holes have also left a mark on something much closer to home, our culture. Let's take a moment to explore how these enigmatic giants have captured the human imagination, inspiring stories, art, and even fear. Imagine the awe and terror a black hole evokes. It's no wonder filmmakers and writers have used them as backdrops for some of the most gripping tales. Movies like Interstellar brought black holes to life with stunning visuals, turning complex physics into an emotional journey. The black hole Gargantua wasn't just a plot device, it was a character, shaping the destiny of those who dared to approach it. Science fiction has long played with the idea of black holes as gateways, traps, or even sentient forces, bending reality to their will. Literature, too, has been fascinated by their mystery. From the poetic descriptions in Carl Sagan's Contact to the chilling void in Arthur C. Clarke's The City and the Stars, black holes serve as symbols of the unknown. They challenge heroes, test human curiosity, and sometimes even offer glimpses into other worlds. Their darkness isn't just emptiness, it's possibility. Artists and musicians have also been drawn to the haunting beauty of black holes. Paintings and digital art often depict them as swirling maelstroms of light and shadow, capturing both their destructive power and strange allure. Composers create soundscapes that echo the vastness and tension of space, making the invisible almost tangible. Even beyond fiction and art, black holes have seeped into our everyday language. Calling something a black hole suggests a point of no return, whether it's a financial sinkhole or an overwhelming project. They've become shorthand for the unfathomable, the powerful, the inescapable. And perhaps that's the real cultural impact of black holes. They remind us that humans, for all our knowledge, still crave stories. We turn cosmic phenomena into myths, into lessons, into reflections of our own fears and dreams. Black holes, in all their terrifying grandeur, are more than just objects in space. They are mirrors, showing us just how vast and full of wonder our imagination can be. And with that thought, we come full circle, from the science to the stories, from the cosmos to the canvas. These cosmic giants don't just shape galaxies, they shape us. As we circle back to the heart of it all, let's take one last look at the extraordinary role supermassive black holes play in the universe. These cosmic titans aren't just destructive forces, they're architects, shaping galaxies, sparking star formation, and even regulating the very structure of the cosmos. From the swirling accretion disks that light up the void to the gravitational waves that ripple through space-time, their influence stretches far beyond the darkness of their event horizons. Yet, for all we've uncovered, so much remains a mystery. How did the earliest supermassive black holes form so quickly after the Big Bang? What happens to the information that vanishes beyond the point of no return? Could these cosmic phenomena hold the key to understanding dark energy, or even the fate of the universe itself? Every discovery seems to open new questions, reminding us that the universe is still full of secrets, waiting to be unraveled. So tonight, when you step outside and look up at the stars, remember, you're gazing at a sky woven together by these invisible giants. Whether it's the quiet glow of the Milky Way's heart or the distant blaze of a quasar, black holes are out there, shaping the cosmos in ways we're only beginning to understand. And who knows, maybe one day, you'll be the one to help solve their mysteries. If you enjoyed this journey through the wonders of supermassive black holes, don't forget to hit like and subscribe for more cosmic adventures. Tap that notification bell so you never miss an exploration into the universe's greatest enigmas. Until next time, keep looking up because the night sky is full of stories and the next chapter is yours to discover.